Hey, Gabriella.
Hello.
Sorry, it just took me a while to connect for some reason this morning.
That's okay. My computer was dead, so I had to grab my charger and stuff too this morning. So it took me a little bit.
Looks like you're the only one who's made the effort this morning.
Woo!
All right. I do appreciate it though. All right, so let's see what we're doing today. I guess we're just doing test review.
Okay.
So let me share.
I did have a random question.
Oh yes.
If we decided to take the final, or if we wanted to take the final, what day would that be?
It would be the Tuesday of finals week at 8 a.m.
Okay, so that's that second week, because I know we have ours, I believe, the first for exam 4 or something.
Well, let me show you here. Hang on. Let me share a screen here, and I'll clear this up for you completely. Okay.
Thank you.
Okay. So for a start, for test 4, that's going to be due December 1st. I believe that's next Tuesday.
Yes.
Okay. And obviously you can get that done before next Tuesday, right? Now the final, I believe that's December 8th, and you can see that, yeah. So you can see the start time there is between 8 a.m. and 9 a.m. Now that's not to say that it's an hour. It's actually much more than that. But you have to start during that time window.
I see. Okay, that makes sense.
Okay, so the floor is open to you. Do you have any other questions?
I think I'm kind of good with the last the second half of the problems from the ungraded copy. I was wondering if we could just do the first.
Oh yeah, let's there. I mean, I was just going to start from the beginning anyway.
Oh, okay, yeah, that works.
and work my way through, but yeah, but since you're here, I just want to make sure that if there was anything else specific that you had that we could go over that.
Not really. I mean, I've just been reviewing, and I think, like I said, I got the second half of it down pretty well, and I think I got the first half pretty well too. It's just since that what we learned first, I just have to review it more.
Well, yes, they call it the recency and the privacy effect, right?
Yeah.
Okay, let's take a look. We'll start from the beginning. So up here, you've got some useful equations. So make sure that you remember that they're there. They will be there on the other one as well.
Okay.
Okay, so for number 1 here, there's, one thing I think I might change at some point is I'm going to probably make it so that one of these on the real test, I'll probably make it so you only get one of these and not both. But the point is that one has remain and one has decay in it, and that makes a difference here as to how you go about solving the problem. Now, the first thing you'll need to do is, well, t half is equal to log 2 divided by k, natural log of 2 divided by k. So we can always calculate k by, and that's little k. Let me make sure I write a little k here. Log 2 over t half, and the half-life is given to you, of course. And log 2 is about 0.693 if you stick it into your calculator. I keep on saying log 2, I mean natural log of 2. And we've got 323.3 hours. Now the figure we get from that, this is for k, it's kind of like the rate constant is what it is. And I get 0.693 0.00214. Now, don't be too concerned about the sig figs on this one. We've got logs involved, and that always throws a spanner in the works as far as sig figs go. 2144, yeah. Now the unit on that is hours to the -1 because it's on the bottom here, and natural log of 2 doesn't have any units. Now, when we're applying the rest of it, you can see we've got an equation up here that helps you with this, and that's negative KT is equal to log A over A0. So the A over A0 here represents the fraction remaining every single time. Since it does say to remain, then we use that number directly. We don't subtract it from 100%. And what we do there is we take that percentage, we convert it into a fraction, because that's what A over A0 would represent. So A is the amount remaining after a certain time. A0 is the initial amount. So that's how we get the percentage there, because it's always part divided by a whole. And that way we end up with a figure that is in hours, and that produces our answer there. So there's two kinds of problems that we're seeing here. One that says remain, and the other one says decay. So if this one had said decay, what I would have done is subtracted the 0.1340 from 1 essentially, and that would have been 0.8660, and that would have been my A over A0, because remained after certain amounts decayed, what's remained is what that is minus from 100%. Is that okay, Gabriella?
Yeah, so for decay, the only difference would be you would do 1 minus.
Yes, that's right.
1.360, and then still divide that by the 0.00.
Yeah, that's the only change. And so that's just the word you're looking for. You're looking to see, does it say remain or does it say decay?
Okay. Does the units change at all for it?
Well, the units will always be, for the final answer, will always match the units on your half-life.
Okay, so it'd be hours. Got it.
Now, the units for K will always be the units for the half-life to the -1.
Okay.
Although, you're not, it never asks the units for K, but I do point that out anyway.
Okay.
All right. Now, the next questions, let me briefly summarize what you're going to have to do here so you can get a little bit more of a big picture of what's going on here. So we got alpha decay, and that's going to be the first two questions. The next ones, I think, are beta minus decay. Then I think it goes beta plus decay. And then I think it goes K electron capture. And then I think it's gamma decay, or gamma decay. And for each of them, there's going to be two questions, and they're all going to require, two questions you'll do will all require the new atomic number, and that's after decay, and the new mass number. Now, in order to do these, you need to know what each of these entails. So alpha decay is loss of, should leave, I'll do it down here. So alpha decay is loss of a helium nucleus. Beta minus decay is loss of an electron. Now, electrons have no mass and a -1 charge. So the atomic number of an electron is essentially -1 because it's the opposite charge of a proton. Beta plus decay is a positron released, and that's 0 again on the mass and +1, so it's the exact opposite of an electron. We've got K electron capture. And that is the absorption of an electron. So the electron is actually on the reactant side. You can see I've been careful where to draw the arrows here in each instance. And gamma decay is release of a gamma particle, which is just a photon. And what's important to note about the gamma decay is there's no change to mass or atomic number. So whatever you start with, you'll finish with. Okay, do you have any questions so far?
No.
Okay. Am I going into too much detail for you?
No, this is good. Thank you.
Okay, good. All right. So let's start with the alpha decay here, and we're starting out with. I'm going to just delete this stuff at the top here. I'll leave the stuff on the bottom because we're going to use that. So you'll notice we've got two questions here. One has to do with atomic number, one has to do with mass number. They are different compounds though, so you have to be cognizant of that. So really it's mostly a matter of just seeing the patterns here, but if we're starting out with, I'll just use this element X here, 78 and 126. Now, if I wanted to, I could figure out what 78 was by going up to the periodic table and then putting that element in, but it's really not necessary. See, it would be platinum, but there's no real necessity here to do anything with it, at least not the element symbol. So it's undergoing alpha decay, and as I discussed, that's going to be, and I really probably should use another letter. Well, maybe I'll just put in platinum here just for kicks. And as I said, we're releasing a helium nucleus. So we know that Y is going to equal 122. And this is a 2 here, not a Z. And that's a Z there. So that would be, the Z there would be 76. There we go. So the answer, if you're looking for the atomic number, would be 76. If you were looking for the mass number, it would be 122. Do you have any questions?
Nope, I think that's good. So it would just be taking away 4 and 2 from those numbers.
Yeah, but you've got to make sure you take 4 and 2 away from the right numbers though, right?
Right.
And the other thing, Gabriella, really important, make sure that you are really aware of what the atomic number is and what the mass number is.
Okay.
The mass number is always on top and the atomic number is always on the bottom.
Right. So then is that like how would you put that answer in? Like
Oh, well, that's what I'm saying. For number 3 here, it's asking for the atomic number. So you would just stick in 76. See, it's not looking for a symbol or anything.
okay, because you don't have to put both. You would just put one or the
Well,
other.
you put whatever you're asked for.
Right,
right. So you'll be asked for both. So the atomic number you'll put in 76. Now I didn't do the mass number, but if you were asked for the mass number, you would have put in 122.
Right.
So you with me on that?
Yeah.
Again, I will use I'll go ahead and find out what this element is, but it's 65 for the atomic number and the mass number is 115. So I can go up here, I can figure out what the element is. Let's see, 65. There we go, that's TB. So let's see, Y here is equal to 111. Oh, no, we're sorry. I'm sorry, Gabriella. We're looking at beta decay.
Yeah,
We're looking at beta minus decay. Sorry about that.
that's okay.
Let's go back and do the right thing here. So E -1, 0. Are you okay with what I've got here on the electron and why it's 0 and -1?
Yeah.
Okay. So the Z here, you've got to be a little bit careful with the Z and see that it's going to be 66 and not 64. Are you okay with that?
Yeah.
Okay, and the Y value isn't going to change. So when asked for the atomic number, it would be 66. When asked for the mass number, it'd be 115. So you're not going to see any change at all in the mass number. Okay. That makes sense because electrons don't weigh anything.
Mm-hmm.
Okay, so the next one, see, that was beta minus decay.
Okay.
This is going to be beta plus decay we're going to look at next, and it's 59 and 124. Now 59, here we go, PR. Now for this one, Z is going to equal 58 and the Y value will be 124, so that won't change. But you'll notice the effect on the Z value. You're okay with that for beta plus decay?
So why is this one 58 and not like 60?
Well, if it was 60, it'd be the total would be 61, correct?
I see. Okay, yes.
You've always got to look at that number and make sure that whatever you put over here adds up or subtracts or whatever. I mean, that was the difference between this and the beta minus decay.
I got it. That's why the one.
No, that's good because if I say, you'd be amazed how many people make that mistake. And it really is just a math mistake. It's math error. That's all it is. Right. It's not really a chemistry error at all.
Right.
Yeah. All right, so are you okay with beta plus decay?
Yes.
All right, now next one is K electron capture. And we've got 73 and 132. So I go back up here, 73, and we've got TA. think it was 122, wasn't it? I think it was. Actually, I'll just go check. I should remember. I mean, it was only 2 seconds ago, but I looked at it. 132. Okay, all right. Now, it's K electron capture, which means that it's absorbing an electron from the inner shell, which means the electron is essentially under a reactant in this case. So that electron actually comes from the TA itself. So the Z value here is going to be 72, because that's just 73 minus 1. And the Y value is going to, again, not change. It's going to be 132. You okay with that?
Yeah.
But the key word is capture. You know, that the fact that it says capture and not decay, anything that says decay, you'll notice is a product. Do you see that?
Yeah.
But if it says, when it says capture, the electron is essentially a reactant.
Okay.
And the last one I'm not going to do is just going to be the gamma decay. Hang on, where are we? Here we go. Okay, electron decay. Yeah, gamma decay. So gamma ray emission. And with that, nothing changes because it doesn't change the atomic number or the mass number.
So it would essentially stay the same. So
It would just be,
when
yes.
it says the atomic number, you just put 64.
Mm-hmm. And the mass number, 115, that's it.
Okay, and that's for the gamma.
Yeah, for gamma, because it's just a photon.
Okay.
It's not an actual nuclear particle. You know, a particle is part of a nucleus, like a proton or electron or part of the atom. It's not a proton or electron or a neutron or anything like that. So for this one, when you're looking for the mass number of element X, again, it's really just a bit of algebra here. You're trying to find the X value that would satisfy this. The only wrinkle here is the neutron. And you'll notice the symbol for the neutron here. I don't show the atomic number as is customary here. But if you look at what a neutron is, it has a mass of 1, but the charge is 0 because it's neutral. But if you've got, say, 2 of them, that means you've got essentially 1 and 0 plus 1 and 0, which means these get added together to form 2. So when I'm doing the math over here, I would put 235 plus 19 equals 84 plus X plus 2. And then I solve for X. Do you have any questions about that?
No, okay, that makes sense. The only part that was confusing was that like 2, 1 end, but now I see why it's 2, so I get that.
Yeah, if it was 3, it would just be 3 of them added together.
Okay.
Yeah, so you're with me on just using that as the number of neutrons and just sort of multiplying it by the 1 here.
Yeah.
Okay, well, that's not too bad, is it?
Nope.
Now, on the real test, I think you just get one of these. I don't think
Okay.
you get both, right?
Okay.
So you'll notice it's the same problem. And what you're trying to do here is determine whether it's proton or neutron rich. I'm going to leave these equations down the bottom here because we might need to reference them a little bit later. But if you look at the wording of the question, what you're looking for is the atomic number of the element it becomes after radioactive decay has occurred. So what we're looking at here is we're trying to determine, well, is it proton or neutron rich? Because if it's proton rich or neutron rich, it's going to either go beta minus decay or beta plus decay. Now I'll go into that in a second. Let's talk first of all about whether it's going to be proton or neutron rich. So we've got 44, 106. So 44 is the atomic number and 106 is the mass number. For this, I actually do need the element because we need it on the periodic table. So 44, there we go, that's Ru. Now the next thing we want to do, this is what we're dealing with, stable Ru is what it is on the periodic table. We've got 44 and it looks like it's 101. So the supposition here, or the assumption I should say, is that whatever's on the periodic table represents at least something around the most stable form of Ru, because the mass number here is always going to be the natural, it's always taken account of natural abundance. So if something is naturally abundant, then that's going to usually be the more stable isotope anyway. So we're just getting it directly off here. Now what you'll see is you want to compare this to the one up here. Let's look at the number of protons and the number of neutrons here. So the number of protons is going to be 44, which matches the atomic number. The number of neutrons is going to be 106 minus 44, which is 62. Now for stable, the number of protons is still 44, but the number of neutrons here is going to be, let's see, 101. That would be 57, yeah. So then what you do is you look at the neutrons and you compare them. And you can see that Ru106, the one we're actually dealing with, has more neutrons than it would if it was stable. This would tell me it was neutron rich, as opposed to being proton rich. Now, had this been less, let's say, had this one up here been less, let's say it was 52 or something, then what you'd say is that it would be proton rich, which is really the same as being neutron deficient. Are you okay so far, Gabriella?
Yes.
Now, if it's neutron rich, it decays in a specific fashion. The two that we're going to be focusing on here are beta minus decay and beta plus decay. Now, beta minus decay, let's have a look at that. We got, remember, we're dealing with 106 and 44. And we're going to, because it's neutron rich, we're going to use beta minus decay, which means that the element we're getting will be 45 and 106. And 45 is RH. The answer you'd put down would be this one. Now, the reason that it undergoes beta minus decay is because it's neutron rich, and a neutron is actually turning into a proton plus an electron because there's too many neutrons. So it's a neutron that's decaying. It's turning into a proton plus an electron. There's your electron there, and the extra proton is what you're seeing over here. It goes from 44 to 45. Is that okay?
Yeah.
You sure?
Mm-hmm.
All right. You didn't sound too sure, Gabriella.
Well, my question was going to be, why do we use beta minus decay instead of beta plus decay? And then you answered it. So.
Oh, okay, fair enough. And you're happy with that answer?
Yes.
All right. Actually, when you look at the other one, this one here, this one, I'll tell you, spoiler alert, is going to be proton rich, but I'll go through and show you the math on it. Okay. And then actually, this one's a little bit more clear as to why it's beta plus decay on this one. And you'll see that that will kind of make you also understand the other one a little bit better too. So this one is 45 and 80. And 45, if we look at the periodic table, is RH. And if we look at stable RH, and I put that in quotes, we've got 103. So again, we do the math here. We've got protons, number of protons is 45. Number of neutrons is 80. And for the stable version, number of protons is still 45. But the number of neutrons is now, what are we looking at? 103 minus 45, so it's 58.
Would you do 103 minus 80, or would it be 80? For like when it's 80, 45, you put
Did I, I'm sorry.
Yeah, like, does it say 80? Okay.
That makes sense. That makes more sense, right?
Yeah.
Okay. For the other one, number of neutrons. Did I get that right? Yeah, I think that's 58.
Yeah.
Yeah. Okay. All right. So what we're dealing with here has too few neutrons, which means it has too many protons. So it would be, you could say it's neutron deficient relative to the one we're comparing it to. But the other way of looking at it is saying that there's too many protons. That's a semantic thing that you have to understand there as well. All right, so let's go back to RH here. 45. Okay, so X, Y, Z plus E. Now this one is going to be positron decay or beta plus decay. And the thing is, if this has too many, are you okay with it having too many protons?
Yes.
Okay. So if it's got too many protons, it makes sense that it wants to get rid of positive charges. And that's what a positron is. It's a positively charged electron. So it's a positively charged species. So what's really happening here is that you've got a proton and it's turning into a positron and a neutron. So it wants to form more neutrons because it's neutron deficient.
Got it.
So that means Z here is going to be 44, and that would be your answer.
Okay.
All right, so do you have any questions?
Nope. That makes more sense now. Like you said, after seeing that one, like why the other one was beta minus.
Yeah. And the mass defect one, that's not too bad. It's really just math again on this one.
Okay.
So the first thing you want to do is figure out what we call the mass defect. Now the mass defect is the difference in mass between the products and the reactants. So what we do is we add up all the masses of the products and we subtract out the sum of the mass of the reactants. On a practical basis, what that means is we take the sum of the masses of C and D and we subtract the sum of the masses of A and B. So I'm going to go ahead and do that. So it'd be 4.1710 minus, plus, I should say, plus 5.1911. And then that's minus 0.1024 and also minus 6.3179. Now the result we get is always a negative number, 0.0582 in this case. And what that's indicative of, and that's in AMU, because that's what it says here. What that's indicative of is that the products weigh less than the reactants do. And that difference in mass is what gets converted into energy. And we can calculate that energy using E equals mc squared. Are you okay so far?
Yeah.
So we do E equals mc squared. And for this, you need to use some information that's above the question. And you can see it up here. This is what 1 AMU is in kilograms. We've got Avogadro's number here as well. And we've got the speed of light. And we're looking for the energy, but it's in gigajoules. Now, that's not usually what we're looking for. We're usually looking for kilojoules. But in order to get an answer that you can more easily put in the box here, I've asked you to convert it to kilojoules, to gigajoules along the way.
Okay.
So the mass here, well, it is point. Now, I'm going to drop off I am dropping off the negative here because the energy is going to be a positive value. It's the energy released.
Okay.
And, that's what you want to put the positive value. See, the energy it's released, not the energy, it's not a negative amount that gets released. Do you see my meaning here?
Yes.
I'm going to drop this down here. It'll be, now we need to convert that into kilograms. So we've got the conversion up here to be times 1.6605 times 10 to the negative 27 kilograms per AMU. Then we've got the C value, that's the speed of light, that's 2.998 times 10 to the 8th, and that's meters per second on the unit, and all of that gets squared. Now, if we were just to stop right there, we'd come out with an energy that's in joules. Now, the unit there is kilograms meters squared per second squared, which is really a joule. So that's what we have so far as a joule. But we want gigajoules. So what I'm going to do, I do have the conversion up here. So it's going to be 1 gigajoule times over 1 times 10 to the 9th joules. And then if we want gigajoules per mole, which means we need to multiply it by Avogadro's number to get the per mole in there. So Avogadro's number is objects per mole. So it's how many particles or whatever there are in a mole. And then that gives us our final answer.
So when we type it in, or in the honor lock calculator, how, would we just multiply all of those things straight to each other, or do we have to do it
Well, let me go through it.
Okay. Because I understand what we're multiplying. It's just I know sometimes if you multiply it or input it the wrong way, it'll give you a different number.
Yeah. Yeah, I'll tell you this. What you're expecting is a value in the hundreds or thousands. If you're not getting even possibly tens, hundreds or thousands. If you're not getting that, it means you've done something wrong.
Okay.
I think that's good to know to begin with. So here's what I would do. Let me clear this out first. 0.0582. Then I would do times. And you'll notice how it goes a darker gray color. That means it's active. 1.6605. And then EE, negative 27, and you use the plus minus button up here. And then I would multiply it. And it's, there's a couple of ways of doing this, but I would just multiply it twice. I'd go times 2.998, again, EE 8, times 2.998 EE 8. So that's the same thing as doing it squared. Right. And then it's divided by 1 times 10 to the 9th. So I'm going to go net divided by 1 E9. and then multiply by 6.022 times 10 to the 23rd. And then hit equals. And there's my answer. It'll be 5230. I know that's right. Or 523, yeah, I'd just make it 5230 would be my final answer there.
Okay.
And that would be gigajoules per mole. Now I know that's, or at least I have a pretty good idea that's right, because it's in the hundreds, it's either in the tens or hundreds or thousands, most likely in the hundreds or thousands. So I'm pretty confident of that answer.
Okay, that makes sense. Yeah, I just wanted to make sure I knew how I was typing it in right, because I understood the math, but I just didn't know if you can go straight across like that, or if we had to cut it in sections. Okay.
Now for that one, I would recommend putting your work down in the bottom box.
Okay.
So that you know, if you do mess up, then at least you know you've shown me that you understand what you're doing, and that you get some partial credit. But
Okay.
But I think if you can be real confident of your answer if you're getting something in the hundreds or thousands. Okay.
Okay.
Okay, now we'll see where we're at here. Concentrations. All right. So the first one here is looking for the mass percent of X, and the mass percent of X, you'd have to know what the formula is for that, but it's just a standard percentage really. It's mass of X is equal to mass of X percent. Sorry, yeah, it's going to be mass of X over mass of X plus mass of Y. And that's all multiplied by 100%. Now we're given here a volume of X. And so the other thing we're going to need is the density equation, so we can switch between mass, volume, and density. So mass is going to be always density times volume, and volume is always mass divided by density. Are you okay with that so far?
Yes.
So for this one, mass of X is going to be 45.00 mils times the density, which is 64.00 grams per mil. Sorry, no, it's not. Where is it here? It's 1.069 grams per mil. Let's make sure I get that right. So you see the mils will cancel, we'll get grams out of that. The Y, we're also going to find the mass of Y as well. And that's going to be 700.00 mils. Again, times the density that we're given, 0.943 grams per mil. And then after that, it's just a matter of putting in the math. Do you have any questions?
No.
Now, keep in mind that every time you go through this, you could get grams or you could get mils. So sometimes you'll need to do that conversion, sometimes you won't. In this case, you had to do it on both.
Okay.
That's why I think it's important for this test to go over it a number of times so you can practice doing it with different combinations.
Right. So you said sometimes it'll be either grams or mils?
That's right. Now this, let's say this was grams.
Uh-huh.
Then you would just use it directly.
Okay.
It's only because it's mils that we have to convert it into grams, because that's what we need. We need a mass of X and a mass of Y here to get this right.
Got it. And that's why we like multiplied the other number just to make sense, or?
Well, because mass is density times volume.
Right. Okay.
Okay, next one, we're looking for the molarity. Now, molarity, and this is something you'll have to know, is molarity. Now, you do have a couple of clues here. We'll do No, you don't. It just says molarity. Okay. So molarity is going to be moles of solute. In fact, I'm going to actually go make that a little bit less general. So moles of X, because we're looking for the molarity of X over liters of solution. Now remember, the solution is a combination of X and Y, if it's a liquid. And or just simply Y if X is a solid. So for this one, it does matter if X is liquid or solid. Now, given, see, you're actually told here is liquid X. Do you see that?
Yes.
If it was solid X, you'd assume that the solid wasn't going to change the volume of the solution very much. Do you see do you see the distinction?
Yes.
Yeah, so molarity is always moles of X over liters of solution, and that's really important to realize. So the moles of X here, well, we're given a volume here. So again, we have to get that mass. So density is equal to mass divided by volume. So mass is equal to density times volume. And the mass here is its mass of X. Is going to be, well, actually, we are actually given that. Hang on, where are we? What number are we looking at? Here we are looking at that one. Okay. Sorry about that.
Okay.
We're actually already given, I was looking at the wrong thing there. I'm sorry about that. I was looking down here. So we are actually given the mass of X as 35.00 grams. So we don't even really need to worry about the density here.
Oh, okay.
And we need to figure out the moles. Now you are given the molecular weight, so 1 mole over 60.00 grams. So this will be moles of X that we're looking for. So that's the first part. Then we need to look at the liters of solution. And as I said, X is a liquid, so liters of solution. Is going to be, let's see, so we've got 725.00 grams of Y. That's the solvent. That one I will have to multiply by the density to get the mass. No, I don't have to multiply it. I'm lying now. So liters of solution. As I had said earlier, density is mass divided by volume. Volume equals mass divided by density. And remember, we want liters here, so that's the only way we're going to get this done. So we'll multiply this by 1 over the density, which is 1 mil and 0.970 grams. Yeah, do you see what I did there? How I flipped the density over?
Yes.
That was because I was dividing by the density.
Okay.
All right, so I get 747 point. Oh, let's see. So it's yeah, it'll be 366. So it'll be 747 milliliters. So let me adjust that. We'll just get liters of Y for now. And that means I have to multiply that by 1 liter over 1,000 mils, which is going to be 0.747 liters. That's just for Y. We also need the liters of X though, because the solution will be X plus Y. So the liters of X here, now what have we got? See, we've got 35.00 grams. So again, I have to do that same thing. And again, it's times 1 over the density, which would be 1 milliliter over 0.994 grams. And that's going to be 37.1 milliliters. And again, we need liters. So we need liters, 0.0371 liters. And then we can, that's it for X. So we need this is going to be X plus Y. Which means I have to add these together. So it'd be 0.747 plus 0.0371 liters. Now understand you wouldn't do that if it was a solid. You would just use the solvent. That would be it. You wouldn't even worry about the volume of the solid. All right. Do you have any questions?
So if it was just Y, we wouldn't add them. We would just use the value of like that number that we got for Y.
Right. And in that instance, it would be because it said solid X here, Gabrielle.
Right. Okay.
Right.
Fine.
And it's kind of makes sense because if you're pouring a liquid into a liquid, you can see the volume change, right?
Mm-hmm.
But if you're putting a solid into a liquid, often you don't really see the volume change. Do you see the distinction there?
Yes. So then for our final answer, we would do like whatever we got for that mole of X divided by
Yes, that's right.
the Y.
Whatever liters you come up with.
Yeah.
Right.
Okay.
And again, you know, you'll see as you go through and do this test again and again, you'll see different versions of that question.
Right.
Sometimes a liquid, sometimes a solid. So you have to be cognizant of both kinds there. Okay, let's look at the next one. The next one you'll see is, if you look at what the final answer is, molality. Now, molality is a little bit different to molarity. Molality is moles of X over kilograms of solvent, which in this case would just be Y in every single case, regardless of whether X was a liquid or a solid. Do you see the distinction there between molality and molarity?
Yes.
Because of the previous one, it was liters of solution. This one is kilograms of solvent, strictly solvent. You sure you're okay with that?
Yes.
Okay. So for this one, moles of X, well, we've already given the grams, but you could be given mils too. So, you know, you need to be aware of that. In which case you would need to convert it using the density. So that'll give you the moles of X. Now the kilograms of Y is going to be 610.00 grams. And again, if it was mils, you'd have to convert it into grams using the density. And you will see examples of that. So it's grams, 1 kilogram over 1,000 grams. And that's it. You would take those two answers and divide them. They'll give you 5 answers.
Okay.
Now, you've got to be real cognizant of these units here, Gabriella. Do you understand if that was mils, you'd have to convert it into grams using density?
Right.
Likewise, if this was mils, you'd have to convert that into grams using density.
Right. Yes.
Okay.
And that would have been the only difference, right? Like if it
Yes. But you got to be prepared. I mean, they're all
Right.
all possibilities are possible. And I think that's what can sometimes happen is people just do this test once and feel, oh yeah, this is how it's going to be. Then of course it changes on the real test, and
Right.
then I get a nasty email saying, hang on, you said this would be the same. Well, I am transparent about the kinds of things you're going to see. All right, the next one, this is mole fraction. Now mole fraction, and we're looking for the mole fraction of X, which is this symbol here, which is going to be moles of X over moles of X plus mole of Y. Now it's not a percent, it's just a fraction. And the moles of X is going to equal the grams of X, which we already have. Keep in mind that could be mils.
Right.
And that's times 1 mole over the molecular weight. And we find the moles of Y as well. And what are we given there? So again, we're given grams, but we could have been given mils there too. And that's times 1 mole again over the molecular weight, 90. And then you do the math there and come up with an answer.
Okay.
So you're right with all of that?
Yes. So for that, the mole of X we would use for like the top and bottom of that?
Yeah, because it's mole of X plus mole of Y on the bottom. So it's a total, it's a fraction.
Okay.
Right?
Yeah, I just want to make sure that's answer that we got from mole of X. We applied to both.
You applied to both. That's exactly right.
Numerator and denominator. Okay.
Yeah, it's kind of like X over X plus Y.
Right.
You sub the X into both. Okay. All right, colligative properties. Now this one is freezing point depression. So what we need, now you are given some equations up here. And the one that's relevant to you is this one, delta TF is equal to KF times M. Now the KF value you given in the problem, mole L freezing constant, 2.571 degrees C per mole L. And that's times the molality, but we need the molality. Now the molality, you have to figure this out separately. Is the moles of X over the kilograms of X. Kilograms of Y, solvent. Now the mole of X, we're going to get this same way, but you'll notice, see how you're given a volume here?
Mm-hmm.
So we're going to have to convert that into a mass first. And we use, of course, this density equation here. Density is mass divided by volume. So mass equals density times volume.
Right.
And the volume is that 55.00 mils, and then that's times 1.038 grams per mil. This will give us grams. And then we need moles, so that would be times 1 mole over the molecular weight, which is 81.00 grams. And then that gives us our moles of X. And we've got the Y here, we need kilograms of that. Now we are again given mils, so 695.00 mils times the given density, 1.167 grams per mil. And we're looking for kilos. See, this will give us grams. We need kilograms, so be times 1 kilogram over 1,000 grams. And that will give us kilograms of Y.
Okay.
And that is where you'll get the molality from.
Right.
I'll do the math on that, actually. So we come up with this something. Let's see, so 55 times 1.038 divided by 81. So I got 0.704 moles of X. And that's 0.8110 on the kilograms of Y. So now I divide those two. And I get 0.868. I probably should have used another significant figure. I'll just go with 0.8680. And that's moles per kilogram, which is also little m over here. So we take that value, we stick it in up here. Now this represents a change in freezing point. I get 2.232. That's degrees Celsius. So that's the delta T after change in freezing point. Now you are given in the problem here the freezing point of the pure Y, which is 1.00 degrees Celsius. So the new freezing point, and you have to know that it's freezing point depression, is going to be 1.00 degrees Celsius minus 2.23. And the minus there is important
Okay.
because it's freezing point depression. And that gives you your answer. All right, do you have any questions?
No, I got that one. I think that one's okay.
Now, boiling point is pretty much exactly the same thing, except that at the end, you take the boiling point of pure Y, which in this case is 47.00 degrees, and then instead of subtracting, you would add that result, the delta TB. See this delta TF, the other one would be delta TB. It's the same formula.
So everything else is the same.
Yeah, everything else is exactly the same.
Too.
And I don't want to go through that again. There's really no need to.
Right. Yeah. No, I got that. If that's the only difference.
Yeah. All right. Do you have any other questions?
Nope.
All right. Now the vapor pressure, you are given the formula for that as well. And that's up here, delta P solvent. Is actually equal to the mole fraction of solute times the P naught of the solvent, which is the pure vapor pressure, which you're given. So for this one, you would have to get the mole fraction. And remember that the chi, in this case, it's x, is what we're looking for. Chi x is going to be moles of x over moles of x plus moles of y. Now we've already gone through and done that. So you'd have to do that for each of these. You okay with that?
Yes.
Now the P naught solvent you're given here, and that's 32.00 torr. So you would take whatever result here so whatever we get here, multiplied by 32.00 torr.
And that would be the final answer.
No, that would be the delta P of the solvent.
Oh, okay, right.
The new vapor pressure would be the P naught solvent minus the delta P of the solvent,
Right.
because it's vapor pressure lowering. So to be 32.00 torr minus whatever we got up here. That would be the final answer.
Right. Okay.
All right, do you have any questions about that?
Nope, that's good.
Okay. And the next one, number 24. This is for osmotic pressure. Now the M is the molarity. So you're actually going to have to find the molarity of X. And this will be a final answer. Once you put it in, you have to subtract it. So you'll notice here, you definitely have a liquid X, and you know that because it's mils.
Mm-hmm.
So the liters of solution will be liters of X plus liters of Y.
Okay. Would that always be the case, or could it be like just Y?
I'm actually not going to say.
Okay.
I'm going to ask you to do this enough times to make that determination yourself.
Okay.
But be aware, if that was grams, you wouldn't add it. It would just be liters of Y.
Right.
Now grams have said solid, and it would have to say solid as well.
Right.
And if it said solid, you wouldn't be given a density either.
Right. Okay.
Is that understood?
Yeah.
If you are given a density, then you know you're dealing with liquid.
Right. That makes sense.
You are given the value of R here in the problem. So that's what you use. And the temperature is in Kelvin. You'll notice that from the R unit. So you convert these 57 into Kelvin. Multiply all that together, that gives you your answer.
Okay. So you just find the molarity and then multiply the others two, make sure we change the temperature. And then
Right. That's right. Yeah.
Okay.
So that's it for that.
That makes sense.
All right. Now you'll notice I did for the coordination chemistry. I'm not going to go through these. We're not going to have time.
Yeah, I remember those pretty well from the last class for the most part, because we're not actually drawing them. It's just the writing them out, which
Right. So I do get. See, you see this? I've actually added this into the test.
Oh, okay. Yeah, I remember you saying that last class.
Right, and you'll notice it's different for octahedral and tetrahedral.
Yes.
So there's still some extra knowledge you're going to need in order to do that, but at least you don't have to memorize the splitting of the D levels.
Right.
All right, so I think we'll leave it there for today, Gabriella.
Okay.
I do appreciate you coming. If nobody had come, I don't know what I would have done.
No, it was helpful for me a lot.
Okay, that's good. Well, I'll still put the recording up, and maybe some people will watch it. We'll see what happens.
Well, I hope you have a good Thanksgiving.
I hope you do too, Gabriella. Stay
Thank you.
safe. All right,
Yes, you
please.
too.
All right.
Bye.
I'll see you later.